extension of range of MI instruments. Okay, we know that directly by using MI instrument alone we cannot measure high voltage and high currents. Why? That is, if you apply high voltage and high currents, then the coil may be damaged. Coil in the sense the electromagnet may be damaged. No doubt at all. Here springs not carrying the current. In MI instrument, springs not carrying the current. But even though springs is not carrying the current, why you cannot measure high voltage and high currents directly means because we are using electromagnet. That electromagnet cannot withstand high voltage and high currents. That's why you go for extension of range. Extension of range is nothing but an indirect method. Directly we cannot measure, then you go for indirectly we can measure high voltage and high currents. But point to remember, for any AC instrument, not only MI instrument, for any AC instrument we can use two methods. One is theoretically, another one is practical method. But here our analysis is theoretical method, not the practical method. Practically means the range of AC instrument is extended by using instrument transformer. That is by using CT and PT. That means one method of extending the range of MI instrument is using instrument transformers. Yes, concentrate all of you. Using instrument transformers. Another method is using shunt resistance and series multiplier. Using shunt resistance S and series multiplier. Shunt resistance and series multiplier. This is two methods, but this is only practical method. Practically we can use this method, and this is theoretically. This method is employed theoretically. But our analysis is theoretical method, not the practical method. But I want to give one or 2 points with respect to practical method. That means using instrument transformers means, which are the instrument transformers? That is using current transformer and potential transformer. For example, if you want to measure the high voltages by using MI voltmeter. If you want to measure high voltages by using MI voltmeter, then what we can do means, in front of this MI voltmeter, we can connect one potential transformer. High voltages cannot withstand this one. That's why in front of this we are using one potential transformer. For example, we want to measure 11 kV by using MI voltmeter. This 11 kV is not directly applied to MI meter. Then in front of this we are using one potential transformer. This potential transformer will step down the voltage. Let this voltage is applied to MI meter. That is the meaning. Point to remember, I already explained extension of range of PMMC instrument. But as compared to PMMC instrument, by using instrument alone, by using MI instrument alone, we can measure high voltage and high currents. Without extension of range, using PMMC instrument, by using instrument alone, how much voltage is measured, how much current is measured, that I already given. But point to remember, by using MI instrument alone, we can measure more range as compared to PMMC. More range in the sense, up to 50 or 100 amperes also we can measure instrument alone by using MI instrument. Okay, that point to remember. Okay, then, but if you want to extend for large range, for example, I want to measure 11 kV, then directly we cannot measure 11 kV. Then in front of this, what we can use? Potential transformer. This potential transformer will step down the voltage. But you have the doubt here, sir, we are applying only 400 volts, but how you are measuring 11 kV? Yes, 11 kV is step down to 400 volts, whatever the we are maintaining step down how much you are making the step down. According to that, we can design one multiplication factor. Then you multiply it with the deflection of a pointer, that gives the exact voltage. That's why it is an indirect method, not a direct method. Okay. Similarly, if you want to measure high currents by using MI meter, then directly you don't apply high currents. Then what you can do? In front of this, we can place one CT, current transformer. In front of this, we can place one current transformer. Okay. For example, the primary of current transformer is, let us assume that 100 amperes. But this 100 ampere is stepped down to 10 ampere. This 10 ampere is applied to MI meter moment. Then it measures the 10 amperes. That is a range of extension by using MI instrument. Here, potential transformer step down the voltage. That's why we are using less number of turns at the secondary. Current transformer step down the current, not a voltage. That's why we are using more number of turns at the secondary. If the number of turns is more at the secondary, then it acts as a step up transformer. If the number of turns is less at the secondary, then it acts as a step down. That's why potential transformer is a step down transformer, current transformer is a step up transformer. That point to remember. But one more point to concentrate, not only MI instrument, for any AC instrument, yes, for any AC instrument, the range is extended practically, yes, practically the range is extended using CT and PT. You take electrodynamometer type instrument, you take wattmeter. For any AC instrument, practically the range is extended by using CT and PT. Then current transformer is used with respect to extension of current. Potential transformer is used with respect to extension of voltage. Okay. This about some introduction, how we are extending the range practically. But in detail analysis is mainly concentrate on theoretical method only. Then using shunt resistance and series multiplier. Shunt resistance is used for ammeter, series multiplier is used for voltmeter. Now we concentrate how to extend the range of MI as a ammeter, how to extend the range of MI as a voltmeter. Clear? Concentrate. First one is MI as a ammeter. Yes. Okay, all of you follow this parallelly. Don't wait. Write down MI as a ammeter. Moving iron instrument as a ammeter. Okay, that you concentrate. Every time drawing the total MI instrument is a lengthy procedure. That's why we concentrate on symbolic representation of MI instrument. Let this is MI meter moment. Parallelly note down, this is MI meter moment. Yes. RM is the meter resistance. LM is the meter inductance. Without any extension of range, it measures the maximum current of IM and it measures the maximum voltage of VM. This is without extension of any range. Then what is RM here? Meter resistance. RM is meter resistance. Lm is meter inductance. Meter inductance. Okay. Then how to write Im equal to, you tell me? Im equal to Vm by Zm. It's not Vm by Rm. But you have one doubt here, sir. In the equivalent circuit reference, in the extension of range of PMMC as a meter, we are not considered inductance, but you are taken inductance here. What is the reason? That I told MI instrument is used for both AC and DC. Once we are using for MI as a MI instrument for AC means you also consider the inductance. If the same MI instrument is used for DC means the effect of inductance is 0 because reactance is 0. Okay, that point to remember. Once we are using for MI instrument for AC means you write Im equal to Vm by Z. If the same MI instrument is used for DC means you can write Im equal to Vm by R. That is the difference. Okay. Now, by using same MI instrument, we want to extend the range from Im to I. Okay. That is, without any modification, it measures the maximum current of Im. This is MI meter moment and Rm is the meter resistance. And what about Lm? Lm is the meter inductance. Okay. Then without any modification, it measures the maximum current of Im. Then by using same meter, we want to extend the range from Im to I. If this high current is allowed through meter, meter will be damaged. Na? Without damaging this meter, we want to measure high current. Yeah, that's why we want to bypass that high current. To bypass that high current, what you can do, tell me? A low value of shunt resistance is connected. Similar to what I explained in PMMC. That is a low value of shunt resistance is connected. Yes. No doubt at all. To extend the range of MI as a ammeter, a low value of shunt resistance is enough. But the problem in MI instrument, if it is used for AC means inductance effect. If MI instrument is used for AC applications, if the frequency is changing, then what are the meter reactance? Meter reactance is changing. Once the meter reactance is changing, what are the meter impedance is also changing. Once the meter impedance is changing, what are the meter current is also changing. Meter current is changing means deviated from the actual value. Deviated from the actual value means that gives the error. Then this error is called frequency error. Yes, this error is called frequency error. This error is called frequency error. That's why in MI instrument, to extend the range, a small value of RSH is enough. But in series with RSH, LSH is also connected. In series with RSH, LSH is also connected to reduce frequency errors. Okay, this is about extension of range of MI as a ammeter. This is I, this is Im, then this current is taken as ISH. Then what is this ISH equal to? I minus Im. ISH equal to I minus Im. Okay, this is the representation of MI as a ammeter. Then what is the purpose of LSH? To reduce frequency. That is, to extend the range of, concentrate, note down, to extend the range of MI ammeter, a small value of RSH is enough. A small value of RSH is enough, but in series with RSH, but in series LSH is also connected. LSH is also connected. That is, but in series with RSH. In series with RSH. In series with RSH. LSH is also connected to reduce frequency errors. To reduce frequency errors. Okay, that is the purpose of connecting LSH. Now the question is, to reduce frequency errors, how much LSH we can connect? That is the design of MI as a meter. Yes, to reduce frequency errors, how much LSH you can connect? Then to design LSH, apply parallel branch principle. These two are parallel branches. Voltage across two parallel branches is equal. Then what is the voltage across meter branch? That is Im into Zm. What is the voltage across shunt branch? ISH into ZSH. Okay, shall you write like this? Then Im into, how to write Zm? Square root of Rm square, because it is impedance na, omega Lm whole square. It's correct. Is equal to, how to write ZSH? That is ISH into square root of RSH square plus omega LSH whole square. Okay, now take Rm square is common, then Im into Rm square root of 1 plus omega Lm by Rm whole square equal to, here I am taking Rm square is common. If Rm square is common, this comes denominator. That's why I am writing 1 plus omega Lm by Rm whole square. That equal to, take RSH square is common. ISH into RSH square root of 1 plus omega LSH by RSH whole square. We are designing LSH in such a way that to reduce the frequency error on the meter. To reduce the frequency error on the meter means LSH must compensate Lm effect. To compensate LSH effect, to compensate Lm effect using LSH, then these two terms must be equal. This is the design procedure. I want to design in such a way that I want to design LSH in such a way that to compensate Lm effect. That's why when this will be compensated, you tell me this term and this term must be equal. That is, to reduce, to make the meter reading is independent of frequency variation. Independent of frequency variation, or to reduce frequency errors. To reduce frequency errors. Then what we can do? These two terms must be equal. Then 1 plus omega Lm by Rm whole square equal to 1 plus omega LSH by RSH whole square. If these two terms are equal, from that what you can write? Tell me. Therefore, Lm by Rm equal to LSH by RSH. This is the condition for to reduce frequency errors or to make the meter reading is independent of frequency variation. What is Lm by R? This is L by R of meter branch now. What is LSH by RSH? This is the L by R of shunt branch now. Meter branch is RL circuit. Shunt branch is also RL circuit now. What is the time constant of RL circuit? L by R. That's why this is the time constant of meter branch is equal to time constant of shunt branch. Okay, this is condition to reduce frequency errors. We can design meter branch and shunt branch in such a way that the time constant of meter branch equal to time constant of shunt branch. Then which errors are reduced? The frequency errors are reduced. That frequency error, or it is also called reactance error. It is also called frequency error, or it is also called reactance error. That's why to reduce the frequency errors or reactance errors in MI as a meter, then tau meter equal to tau shunt. Then what is this LSH value? Tell me. This is the design of LSH. LSH equal to, yes, LM by RM into RSH. Okay. Like this, we can design the LSH value to reduce which errors? Frequency errors. Okay. These are the conditions to reduce frequency errors in ammeter. To reduce frequency errors in MI ammeter. In MI ammeter. That you concentrate. Quick, no doubt. Yes. Now the question is, sir, frequency errors we are getting because of inductance, meter inductance. But you are telling that frequency errors are reduced by connecting LSH. Errors are due to inductance, but again you are telling that you connect LSH. Yes. How it is possible? That you will see. How this LSH will reduce the frequency errors. That you concentrate. Okay, you note down as a note. As a note. First one. For example, let us assume that if the frequency is increasing, or the meter reactance is also increasing, or the meter impedance is also increasing, or the meter current is reduced, then this error is called which error? Frequency error. Because of change in frequency, meter current is changing now. That's why it is called frequency error. Then to reduce this frequency errors, what we are adding? LSH we are connecting. One observation. If LSH is not present, there is no any frequency effect on the shunt branch. But whenever LSH is also added, there is a frequency effect on not only on meter branch, there is a frequency effect on the shunt branch also. Clear? Now, because of LSH on shunt branch, if the frequency is increasing, the shunt reactance is also increasing. Tell me, if the shunt reactance is increasing, what about the shunt impedance? Shunt impedance is also increasing. When the shunt impedance is increasing, what the shunt current reduces. Clear? Concentrate. If the shunt current is reduces, here for a given supply voltage, current is constant. If the supply is changing, then only input current is changing. But here we are maintaining the voltage is constant. Let the voltage is constant we are maintaining. The voltage is constant. If the voltage is constant, whatever the current is also constant. If current to maintain current is constant according to KCL, what is happening? ISH is reducing. If ISH is reducing means what about IM is increasing? IM is increasing to satisfy KCL. Because of frequency error, IM is reduces now. This is called frequency error. Because of LSH, this reduced current again increase now. Understood or not? Reducing nothing but a reduction of, for example, let us assume that initially current is 10 ampere. Meter current is 10 ampere. Now because of frequency error, now the current is 8 ampere. How much error? Error equal to 2 amperes. Error is 2 amperes. Now because of LSH, this IM is increased. Now the IM is increased to 9.5 amperes. Now what is the error? Now error equal to how much? Now error equal to 0.5 amperes. Without shunt inductance effect, then what is the error? 2 amperes. With the shunt inductance effect, error is reduced. Okay, that is the purpose of using LSH. That's why using LSH, what happening here? Using LSH, reduced current is compensated by increased current. Okay, due to LSH, reduced current reduced current due to reduced current is compensated by increased current. That is frequency compensation. That is frequency error compensation. Like this, we are reducing frequency errors by connecting which one? LSH. Okay, that you concentrate. Quick note down. Concentrate one more note here. If the frequency errors are neglected, one more note. If the frequency errors are neglected, no need of connecting LSH. No need of connecting LSH. No need of connecting LSH. Once LSH is not connected, what the equivalent circuit you tell me? Okay, this is the MI meter moment. Then this is meter resistance, MI meter inductance. Then we are not connecting LSH, we are connecting only RSH. This is RSH. This current is I. This current is IM. Meter current is always IM. This is I minus IM. This is equal to ISH. Then from this you design ISH, you tell me. That is, sorry, design RSH. Then ISH into RSH equal to IM into ZM. IM into ZM. Then what is ISH? I minus IM into RSH equal to, that equal to IM into ZM. Clear? Then from this, what is ZM? I by IM minus 1 into RSH is equal to ZM. What is I by M? I by M, high current by low current, is nothing but a multiplying power or multiplying factor. Power or multiplying factor. Then how we can write? That is M minus 1 into RSH is equal to ZM. Then what is RSH equal to? Similar to that of PMMC, ZM by M minus 1. Where M equal to I by IM. This is called multiplying power or multiplying factor. Yes, multiplying power or multiplying factor. Okay, this is the design of RSH. Okay. One more observation. This first one. This is second note. The third note. If MI is used for DC, then if it is used for DC means this is MI meter moment, and this is meter resistance, and this is meter inductance. Then no need to consider meter inductance, because for DC reactance is 0. Then how to write IM equal to? Then IM equal to, you write VM by RM, is not VM by ZM. Then how to write RSH equal to RM by M minus 1. It is not ZM by M minus 1. See the difference. If it is used AC, then you take ZM by M minus 1. If it is used DC, then you take RM by M minus 1. Clear? Okay, this about the points you remember with respect to MI as a ammeter. With respect to MI as a ammeter, RSH is connected, but along with RSH, LS is also connected to reduce frequency error. Then what is that LSH value? LSH equal to LM by RM into RSH. That is, what are the conditions to reduce the frequency errors? LM by RM equal to LSH by RM. That is tau meter equal to tau shunt. Okay, that points you remember. Okay. Then if the frequency errors are neglected, no need of connecting LSH, then what is RSH equal to Zm by M minus 1. If the same meter is used for DC, then in meter also you don't consider any inductance, then you can write RSH equal to Rm by M minus 1. Clear? Concentrate. Main important formula is Lm by Rm equal to LSH by RSH to reduce the frequency error or to make the meter reading is independent of frequency variation. Clear? Okay. Now this is the concept of MI as a ammeter. Now I want to explain what exactly, how to extend the range of MI as a voltmeter. Okay. Next, slow down. MI as a voltmeter. Yes, concentrate. Yes, MI as a moving iron instrument as a voltmeter. How to extend the range of moving iron instrument as a voltmeter? Okay, same concept. Without any modification, let this is MI meter moment. The meter resistance is Rm. Next, the meter inductance is Lm. The meter inductance is Lm. Without any modification, it measures the maximum current of Im and it measures maximum voltage of Vm. Okay. Now, by using same meter, we want to extend the range from Vm to V. Same concept what I discussed in PMMC also. But high voltages are applied, current is increased. If the current is increased, meter may be damaged. Okay. Here, where V greater than Vm, na? Where V greater than Vm. Then if voltage is increased, then what about the current is also increased, then meter is damaged. Meter is damaged. For Im current, it measures the maximum current of Im, means for Im current it gives the full scale deflection. That is the meaning. For Im current it gives the full scale deflection. Again, if high currents are passing through meter, meter will be damaged. Now, we want to measure high voltages without damaging meter. If you want to measure high voltages without damaging meter, means we want to limit that high current. To limit that high current, what we can do, similar to PMMC, a high value of series resistance is connected. A high value of RSC is connected. A high value of RSC is connected. Yes. This about MI as a voltmeter. This is Vm, this is V. Then what this voltage? V minus Vm. Yes, no doubt at all. To extend the range of MI as a voltmeter, a high value of RSC is enough. But the problem in MI instrument is same concept what I discussed in ammeter. If the frequency is changing, meter reactance is changing, then meter impedance is also changing, then meter current is also changing, then this error is called which error? Frequency error. This error is called frequency error or reactance error. That's why practically along with RSC, across RSC, you also connect one capacitor. The purpose of using capacitor is to reduce frequency errors. This what exactly MI as a voltmeter. That means to extend the range, note down this, to extend the range A high value of RSC is enough. A high value of RSC, series resistance, is enough. But across RSC, a capacitance is connected. Yes, a capacitance is connected. What is the purpose of connecting capacitance? To reduce frequency errors. To reduce frequency errors. To reduce frequency errors. That is the purpose of connecting RSC. But one note you remember here. Don't connect capacitor in series with RSC. Sir, how this capacitor will reduce frequency errors means? One simple way to analyze. Capacitance will offer negative reactance. Inductance will offer positive reactance. This negative reactance will reduce the effect of positive reactance. Then we can reduce the frequency errors. But don't connect capacitor in series with RSC. One note you remember. Don't connect capacitor in series with RSC. Capacitor in series with RSC. Why the don't connect capacitor in series with RSC means? The reason is this one. For example, if you connect, this is MI meter movement, RM is the meter resistance, yes, LM is the meter inductance, RSC is the series resistance. Then if you connect capacitor like this, we know that MI is used for both AC and DC. Na? For example, if this is used for DC supply, for DC at steady state, capacitor acts as an open circuit. Capacitor acts as an open circuit. Once it acts as an open circuit, is there any closed path for flow of current? No. Then meter cannot work. That's why to make the meter is universal. Universal in the sense, in order to design for both AC and DC, in order to use for both AC and DC, always capacitor is connected across RSC. If the capacitor is connected across RSC, then even though we can apply DC, then it acts as an open circuit, then path is available for flow of current, then it works for DC also. That's the reason why don't connect capacitor in series with RSC, always capacitance is connected across the RSC. To make the meter is universal in order to use for both AC and DC. If it is not, if it is connected in series with RSC, for DC, capacitor acts as an open circuit, then meter cannot work. That point you remember. Clear? Okay. This about what exactly MI as a voltmeter. Now the question is, what the design of MI as a voltmeter? Yes, to reduce frequency errors. To reduce frequency errors. To reduce frequency errors. What value of capacitance you can connect? That is the design of MI as a voltmeter. To reduce frequency errors means to make the meter reading is independent of frequency variation. Then to design capacitance value, then apply the, write the Z equivalent here. What is the equivalent impedance you tell me? The Z equivalent equal to, how to write? Yes, RM plus J omega Lm, yes, J omega Lm plus this RSC and capacitance is in parallel. Then how to write parallel? RSC in parallel with capacitance. Capacitive reactance is 1 by J omega C. Then what the Z equivalent equal to? Z equivalent equal to RM plus J omega Lm. J omega Lm. You simplify this, RSC into 1 by J omega C by RSC plus 1 by J omega C. Okay, then simplify this. What the Z equivalent equal to? This is calculation of C. RM plus J omega Lm plus, how to write? RSC by j omega c RSC plus 1. Multiply and divide by complex conjugate. What is the complex conjugate of 1 by j omega c RSC? 1 minus j omega c RSC by 1 minus j omega c RSC. Multiply and divide by complex conjugate. Then what is the Z equivalent you can get? Tell me. Z equivalent equal to is Rm plus j omega Lm plus. Then write like this, RSC minus j omega c RSC square by 1 plus omega square c square RSC square. This is RSC minus j omega c RSC square. 1 plus j omega, 1 minus j omega. That you write 1 plus omega square c square RSC square. For approximate analysis, tell me. Omega square c square RSC square very much less than 1. Why taken omega square c square RSC square is very much less than 1 means practically the capacitance value is in picofarad. Picofarad square means you can get 10 to the power of minus 24. That's the reason why as compared to 1 this is negligible. Here I am writing as a approximate. Then if you take approximate analysis, what is the Z equivalent you tell me? Yes. What is the Z equivalent? Then Z equivalent equal to yes, Rm plus j omega Lm plus RSC minus j omega c RSC square. This I am writing. This is neglected. Okay. Then Z equivalent equal to Rm plus RSC plus j omega Lm minus c into RSC square. This is correct. Then to reduce frequency errors, then in this to make the meter reading is independent of frequency variation, which term we can equate to 0? Imaginary term. That's why what is imaginary term here? Lm minus c into RSC square equal to 0. What is the c equal to? Lm by RSC square. Okay, this is the c value to reduce which errors? Frequency errors. The value of c equal to Lm by RSC square. This value of c you can connect across RSC to reduce frequency errors. This is approximate formula, not exact, because I am calculated this value with assumption of approximate analysis. That's why it is approximate. Then if you do exact analysis, means you don't neglect this one. If it is not neglected, you simplify this one, we can get one quadratic equation. By solving that quadratic equation, then you can get c equal to 0.41 Lm by RSC square. C equal to 0.41 Lm by RSC square. Okay, this is exact value. Okay, this value of capacitance we can connect across RSC to reduce frequency errors. In option, both are given, then your answer is exact, not approximate. This we can select. Clear? Already asked in competitive exam based on this formula. To reduce the frequency errors in MI as a voltmeter, what we can do? We can connect capacitor across RSC. What that value of capacitance? C equal to 0.41 Lm by RSC square. If both are given, you select the exact value. If exact is not given, then you take the approximate value. Clear? In MI as a ammeter, how we are reducing the frequency errors? By connecting LSH in series with RSH. In MI as a voltmeter, how we are reducing the frequency errors? By connecting the capacitor across RSC. Clear? Okay. This about design of MI as a voltmeter. Quick note down. Yes, here I want to write one note that you concentrate. If the frequency errors are neglected, similar to what I discussed in MI as a meter, that you concentrate. If frequency errors are neglected, if frequency errors are neglected, then no need of connecting capacitor. Okay, no need of connecting capacitor. No need of connecting capacitor. If the frequency errors are neglected, no need of connecting capacitor. If capacitor is not connected, what is the equivalent? Okay, this is MI meter moment. RM is the meter resistance. LM is the meter inductance. RSC is the series resistance. Okay. Then this current is IM. Then what this voltage? VM. Okay. Then what this voltage is? V. Then what this voltage? V minus VM. Now we want to design RSC. Shall we write like this? Vm by Zm equal to, in series branch current is constant. Whatever the current is passing through meter branch, the same current is passing through series branch. Vm by Zm equal to V minus Vm by RSC. Then from this, RSC by Zm equal to V by Vm minus 1. What is V by Vm? Multiplying factor or multiplying power. Then RSC equal to Zm into M minus 1. Okay, this is the design of RSC. Okay, RSC equal to Zm into M minus 1. If the frequency errors are neglected, no need of connecting capacitance, then we can design RSC equal to Zm into M minus 1. One more note. If MI is used for DC, then this is MI meter moment. Then RM is the meter resistance. Then LM is the meter inductance. Then RSC is the series resistance. Then no need to consider LM. Then what is IM? You tell me. Then IM equal to, then VM by is not Zm. Then IM equal to VM by RM plus RSC. Like this you write. If it is used for DC, no need to consider the meter inductance. Then in this case, what is RSC? RSC equal to RM into M minus 1. Similar to that of PMMC. RSC equal to RM into M. Okay, this about in detail what exactly the extension of range of MI instrument. MI as a ammeter, MI as a voltmeter. In the case of MI as a voltmeter, mainly 2 points you remember. How to reduce the frequency error? By connecting capacitor. And don't connect capacitor in series with RSC. Always you can connect capacitor across RSC. The reason I told. Okay. Then what is the value of C? C equal to Lm by RSC square. That is approximate value. What is the value of C? C equal to 0.41 Lm by RSC square. Okay. Then if it is frequency errors are neglected, what is RSC? Then if it is used for DC, what is the RSC? Okay. With this, the extension of range of MI instruments is complete. Okay. With respect to MI instrument, I discussed about construction details. Based on the construction details, I already given some points and I already explained what is the operation of MI instruments also I given. I derived the torque equation. Based on the torque equation, I given some observations. Then how to extend the range of MI instrument. All these are the concepts with respect to MI instrument. Then based on this, we can solve some classroom workbook questions. With this, MI instrument will be completed. Clear? Concentrate. Thank you. In the next session, we will continue.